Alright, so welcome back. I'm going to pick up where I left off. I am going through the BC version of the multiple choice questions, however a lot of them are the same questions that were on the AB one. So if I get to a BC question, I just won't call on Jin. We get a final head count, see who we've got in here. Okay, so I've got Jin and Kyle and Andrew. Can you guys hear me?
Yes.
Cool. So I'm going to go ahead and start with Jin then, because I think this one can work for AB or BC. So starting at 17, we've got a twice differentiable function shown here. I want to know which of the following is true. So I'm relating my y value to the derivative to the second derivative. So starting with Jin, looking at our graph, what is my y value when x is 1? Hello?
Hello.
Okay, I've got 4. Okay, I'm not sure Jin has a microphone, so I'm going to jump to the next person. So let's go, Kyle, what's our y value when x is 1?
Mr. Brandon,
Yes.
Jin messaged in the group chat.
Oh, I see.
He wrote
Okay.
it there.
How do I see that? I think that's over here. 0, perfect. Okay. Let's do this then. And is there a way I can hide the video? I don't see. That'll work. Okay. So y value when x is 1 is 0. Is our first derivative, so over to Kyle, going to be positive or negative?
Negative.
Okay, so first derivative is the slope. So at the point x equals 1, is our function increasing or decreasing?
Increasing.
Increasing, so the slope should be
Positive.
positive, so that means our slope is greater than 0. And Andrew, looking at the concavity, are we concave up or concave down?
Concave down.
Okay, we are concave down. So that means my second derivative should be greater than 0 or less than 0?
Less than 0.
Less than 0. Okay, so now I've got to order these from this like least to greatest. So if f prime prime is less than 0, then that should be least. F prime prime at 1 will be less than, okay, then I've got f at 1, which is equal to 0, which is less than my positive value, which would be f prime at 1, which is D. Any questions on this one? Okay, I'm going to draw our chart again for people who weren't here last time, so really quickly. If our first derivative is greater than 0, so that means we are increasing. If our first derivative is less than 0, we are decreasing. If our second derivative is greater than 0, then we are concave up. And if our second derivative is less than 0, we are concave down. So if I wanted to graph a function that would look like each of these parts, to be concave up and increasing, I would look like this. To be concave down and increasing, I would look like this. Concave up and decreasing, so I have to be going down but curving upwards as I go down, would look like this. And then concave down and decreasing would be curving downwards as we decrease. So our information about our first and second derivative can tell us the shape and whether or not we're increasing. Okay, BC only, so I'll have Jin sit this one out. Starting with Eric, I want to know whether or not these series will converge. So starting with number 1.
It will diverge.
Okay, it will diverge, you're right. How do you know?
the limit comparison test.
Limit comparison test. Limit comparison to what?
1 over n.
I can't do a limit comparison to 1 over n because right now I've already got n over n. If this had been 1 over n plus 2, then I could do an LCT to 1 over n. So you're right, it's going to diverge, but I need another test.
DCT?
Not direct comparison either. Opening up to anyone else.
Nth term test.
Nth term test, right. So, number 1 diverges by nth term. As long as our limit of our sequence is not 1, then the whole series will diverge. Okay, number 2, going for Kyle again.
I wrote converge by AST.
Okay, it is going to converge by the alternating series, you're right. And for number 3, Andrew.
Number 3 will diverge by P series.
Perfect. Diverges by P series. P series test. Okay, so I want to know which of the following converge. 2 is the only one that converges. If I go back to number 2 really quickly, who do I have left? I've got Eric again. So, Eric, does this converge conditionally or absolutely for number 2?
Conditionally.
Okay, it converges conditionally, you're right. Why does it converge conditionally?
Conditionally to 1 over n. P series stuff.
Okay, so as the P series 1 over n diverges. So it only converges because we are alternating. Awesome. Number 19 is also BC only. Sorry, Jen. I'm going to skip 19 then. We'll do 20 first and come back to it. So for 20, when x equals 8, the rate at which the cubed root of x is increasing is 1 over k times the rate at which x is increasing. So I want to know what the value of k would be. So if I wanted to set this up, trying to figure out where I have space, I guess here on the left. Whenever my x value is 8, the rate at which my cubed root of x is increasing would be 1 over k times the rate at which x is increasing. So if I derive the cubed root of x at the point x equals 8, that should be equal to 1 over k times the derivative of x is what the question's told us so far. Again, only true when x is 8. So jumping over to Jin. Jin, what's going to happen when I derive the cubed root of x? Okay, 1 over 3, x raised to the negative 2/3 power. Perfect. So if you want to type that for a math class later on, you can put your fractions in parentheses like this. So 1 over 3, x raised to the, and then put that in parentheses, and know that this is all part of your power. So like that would be a standard way to write, but that's good. So jumping in here, this is 1/3 x to the negative 2/3 power should be equal to, we were told we are 1 over k times the rate at which x is increasing, so that's 1 over k times the derivative of x. Jen, again, what's the derivative of x? One. Okay, so 1/3 x to the negative 2/3 power should be equal to 1 over k times 1. I'm going to plug in x equals 8, and we'll keep going from there. So jumping over to, we just had Eric, so Kyle next. Kyle, I'm going to plug in x equals 8. When I do, how should I write this? So this should be 1 over 3 times what?
One over 3 times. If we put 8 in?
Yep.
Oh. 8 to the power of 2/3?
2/3 equals 1 over k, okay.
Mm.
So now I need to know what 8 to the power of 2 over 3 is. So this over 3 means I can take a cubed root. So Andrew, what's the cubed root of 8?
4?
Not 4, no. Oh, I think you did all of the 2/3, maybe.
Yes.
Okay, sorry. Yes, so 8 to the 2/3 power would be 4. The cubed root of 8 is 2, and then squared is 4. So this is 1 over 3 times 4 is equal to 1 over k. So therefore 1 over 12 equals 1 over k. So what is k?
12.
12. Oops. K is equal to 12. Any questions on 20? Okay. Jumping to 19, we've got an area of the region inside the polar curve of 4 sine theta and outside the polar curve of r equals 2. Is given by which of the following equations? I think I'm going to cheat and graph on Desmos really quick so we can see what's going on. Let's see, that was 4 sine theta and 2. Again, radians and polar road. We want to be inside 4 sine theta and outside r equals 2. Okay. So if I am inside the region of r equals 4 sine theta, so that means I'm inside the red graph, but I'm outside the blue graph, then I'm really looking at this area here in yellow. So I'm going to call region R. Okay, so I want to find this region R. What do I have to do? Starting with Andrew next.
I have to find the intersection of 4 sine theta and r equals 2.
Okay, in that case, 2 is equal to 4 sine theta. So therefore 1/2 is equal to the sine of theta. I'm just going to write t for now. So therefore the arc sine of 1/2 is equal to t. Going over to Jin. Jin, what is the first angle on the unit circle where the sine is equal to 1/2? Uh, 1/6 times pi. Okay, cool. So that's pi 6. Pi over 6 is the first angle we want. So that means pi 6 is going to be our first intersection point, where these two are equal to each other. However, go a little bit bigger than that maybe. However, Eric, we don't just have one intersect, we've got two. What's our second time where the sine will equal 1/2 on the unit circle?
Um, 7 pi over 6.
Not 7 pi over 6, no.
I want 5 pi over 6.
5 pi 6, perfect. Okay, so I've got A, which is pi 6, and B, which is 5 pi 6. Okay, so if I wanted to set this up and be able to get the area of region R here in yellow, how do I need to set up my area equation? Kyle?
So the area the area equation is A is equal to 1/2 AB fx. So if the area for R would be A is equal to 1/2 from the integral of pi over 6 to 5 pi over 6. And since it's squared on the inside, it's 16 sine squared theta minus 4 d theta.
Okay. Try to copy that really quick. So this is times the integral from pi 6 to 5 pi 6 of, sorry, say one more time. What was your equation?
4 sine theta squared minus 2 squared. Yeah.
Okay, in terms of which variable?
D theta.
D theta, perfect. All right, looks awesome. So now we just need to match that to one of our answers here. So I'm going to throw this over on the right, and we'll see if we can match. Okay, we don't have a direct match anywhere, but which of these do you think matches your answer?
D.
D,
As in
perfect.
dog.
Okay, I'm gonna write our process over here in the corner really quick, so that I can post this later. Let's change colors so I don't run into the other one. This is, we set these equal to each other. 2 is equal to 4 sine theta, so therefore all right. I'm going to skip 21 because that's also BC only. 22 is also BC only. I think I might just skip all the BC only ones and come back to those in the last half hour or so. So that way I don't have to keep Jin through a bunch of stuff he doesn't actually need for the midterm. So skipping to 23. We have a function that's defined and continuous on a closed interval from a to b. If our function f has a relative maximum at c, which is at some point inside of our interval, then I want to know which of the following statements must be true. Andrew, I believe we're over to you. So let's just go through each statement and you can tell me if it must be true. So starting with number 1, our derivative must exist. Is that true or false?
True.
Okay, so this one's actually false, but can you tell me why? Or give me a counterexample.
Why?
So we know our function is defined, we know it's continuous, and we know it has a relative maximum. That's all we know, though. So can you give me a counterexample for a function that would be defined and continuous on an interval, where the derivative would not exist?
Piecewise function.
A piecewise function is perfect. Anytime we've got a cusp where the slope is going to be different at one side of your limits than it would be at the other side of your limit, it could still be continuous. Cusp. We could still be continuous, but our slopes would not approach the same value from the left and the right, which is another condition that we need in order to be differentiable. So number 1 is not necessarily true, because we can have functions that are defined and continuous and have relative maximums without necessarily having a derivative at that point. Number 2. As long as the derivative exists, then the derivative must be equal to 0. I'm going to jump to Jin. So Jin, do you think this will be true or false? Our function is defined, it's continuous, f has a relative maximum at c, and the derivative exists now. Okay, so this is true. You're right. As long as our derivative exists and we have a relative maximum at that point, then the slope must be 0. By definition of a relative maximum, our derivative would be 0 if it exists. Okay, for number 3, if the second derivative exists, then the second derivative must be less than 0 or equal to 0. Eric, what do you think?
True.
Okay, this is true as well. Can you tell me why? Or what part of this told you that this is true?
Because it's in maximum and
Perfect. If we have a relative maximum and our second derivative exists, then that relative maximum should be concave down. Alright, so I want to know which statements must be true. So 2 and 3 must be true. So that is E. Any questions on 23?
what if the graph was like the example you drew for number 1?
If our second derivative exists, then it can't be.
Okay.
So if they didn't have this extra part, then number 3 would be false. If they didn't have this extra part, then number 2 would be false.
Okay.
Okay, good question though. Okay, the 24 is both AB and BC, but this is Kyle's turn. So shown above, we have a slope field for some differential equation. Kyle, what's the first information about this graph that you might look for to help you out?
The first thing I looked at was the horizontal lines.
Horizontal lines. Okay, so for all of these horizontal lines, which are happening here, our slope should be equal to 0. So right now our slope is 0. Dy over dx equals 0 if our x value is equal to our negative y value. Okay, so I'm going to see which one of these derivatives would that be true for. So we'll see if we can eliminate anything with the information Kyle just gave us. Kyle, if x is negative y, our slope is 0. So is that true for A?
No.
No. B?
No.
C?
Yes.
Yes. D?
No.
No. And E?
No. No.
Okay, so that was fast. Okay, we've got an improper integral. That just means we're integrating to infinity. I'm going to start with Jin on this one. Jin, if you wanted to try to use U substitution for this, what would your U be? X squared. Okay, if I make U x squared, then U prime is 2x, and that doesn't eliminate all of my x's, so I'm going to try something else. To give one more guess? E to the negative x cubed. E to the negative x cubed, if I derive that, would be e to the negative x cubed times negative 3x squared. I don't have the extra e to the negative x cubed out there, so I don't think that's going to work either. Let's try one more. There's one more thing we can put for you. Negative x cubed. Okay, that's it. So if we make our u negative x cubed, then our u prime would be negative 3x squared, which is the right power of x squared, so the only difference I have is a constant here. So that means if I make a u substitution, then this would need to be the integral of negative 1/3 times negative 3x squared e to the negative x cubed, or negative 1/3 times the integral of e to the u prime. I'm dividing by negative 3 so that I can multiply by negative 3 without changing the original problem in order to get the negative 3x squared that you need for u prime. in order to substitute for u prime. Any questions on our u substitution? Okay, jumping back to Andrew. Andrew, what's going to happen when we integrate this?
It will be negative 1/3 times e to the negative x cubed power.
Okay, you're right. So this would be e to the negative x cubed, which was our u plus... Oh wait, sorry. We had bounds, didn't we?
Yes.
From 0 to infinity. So I've got two options here. I can either integrate this indefinitely like I just did, and then go back once we've resubstituted for x and plug in our bounds, or you could change your bounds to be in terms of u, which would make this still 0, and if u is negative x cubed and x is infinity, then u would be negative infinity then when I go to plug in. And that would work for substituting in for u instead of x. I'm going to go ahead and integrate this indefinitely, but then plug in my bounds. So if I do, this will go back in terms of x, and I don't need to change my bounds. So this is negative 1/3 times e to the negative infinity cubed minus our lower bound of negative 1/3 times e to the negative 0 cubed. Jumping to Eric, what's going to happen to our left term?
It will be negative infinity.
Not negative infinity, no. Maybe you're talking about the power? My power will become negative infinity, but if I raise e to the negative infinity power, what does that become?
Oh, e to the 0.
E to the negative infinity power is the same thing as 1 over e to the positive infinity power, which is... what will this approach?
0.
0. So this is really 0 times negative 1/3, or 0 for my upper bound. Okay, then I've got a negative and a negative, so this will become a positive 1/3 times, what is e to the negative 0?
1.
1. Anything to the 0 power is 1, so this is 1/3 times 1, really, which is c. Any questions on 25? Okay. Population, logistics. I think this could technically come up in AB as well, so let's go ahead and do this one. Our population of a species satisfies our differential equation dp over dt is p times 2 minus p over 5,000. The initial population is when t is 0, our population is 3,000. I want to know what is the limit as t approaches infinity of our population, so what's our maximum population? Now, it is possible to solve this with a shortcut that I don't think I've taught either class yet. Because I haven't taught you the shortcut, we would need to solve this with a separable differential equation, I believe. So in that case, what's our first step? Forget who we're on. I think we're on Kyle, maybe. Kyle, what's our first step if I want to solve this separable differential equation?
Integrate?
Okay, before I can integrate, I need to make sure that all of my variables are separated.
Distribute p to p to 2 minus p over 5,000.
Okay, I could. I think I'm going to end up refactoring that out though, so I won't do that right away. Right now I've got p's on the right, but I've got p's and t's on the left. I need to change that first.
Solve for p.
Ultimately, yes, but in order to solve for p, we've got some steps we need to do first. So I'm going to open up to anyone. What will our next line look like?
One over p plus p over 5,000 dp equals 2 dt.
Okay, on the right track, we need to separate our variables. I can't split that 2, unfortunately.
Oh, okay.
But that was almost perfect. I think Jin's trying to type out for me. Oh, thought he was. So there's dp over, this would be p times 2 minus p over 5,000 is equal to dt. Okay, and that separates our variables, so we've got all our p's on one side and all of our dt's on the other. From that point, from this point, we could solve this as a partial fraction decomposition problem, essentially. So if I wanted to do that, this would become something like this. I have dp over p times 2 minus p over 5,000 is equal to something over p plus something over 2 minus p over 5,000. Equals dt. It does look a little bit ugly. If I wanted to get rid of that 5,000, I could multiply through by 5,000 on top and bottom and try to get rid of it that way, but I think I might actually leave it. Okay, I'm going to leave it like that. So if I cross multiply right now, then a times 2 minus p over 5,000 plus b times p should be equal to dp, or 1. So 1 must be equal to a times 2 minus p over 5,000 plus b times p. And this equation must be true for all values of our population. So you can pick any value for p that you want and plug that in order to solve for a or b. Going over to Andrew, what's one value of p that you could plug in that would make it easy to solve for either a or b?
0.
Okay, so if p equals 0, then our equation becomes 1 is equal to 2a plus 0. So what is a?
1/2.
1/2. Okay, a little bit harder. What's my other value for our population that we could pick in order to solve for b instead? Eric.
10,000.
10,000, perfect. If I pick 10,000, this will be 2 minus 2, gives us 0 for our a. So I have 1 is equal to 10,000 b. So therefore, 1 over 10,000 is equal to b. Okay, with all of that, we can substitute. So I've got 1/2 times 1 over p plus 1 over 10,000 times 1 over 2 minus p over 5,000 is equal to my other side, which was dt. So if I want to integrate both sides, it would look like this. The integral of dt is equal to 1/2 times the integral of 1 over p plus 1 over 10,000 times the integral of 1 over 2 minus p over 5,000. Okay, over to Jin. Jin, what happens when I integrate 1 over p? Natural log p, perfect. 1 over 10,000. Okay, and then where are we on? We are on Kyle. What happens when I integrate 1 over 2 minus p over 5,000?
Can we also do natural log?
We can also do natural log, but we need to use substitution first. So if u is my whole bottom part, 2 minus p over 5,000, then what is u prime?
Prime is equal to 2x? Is it what variable are we using?
Sorry, say that one more time. It broke up a little bit.
What variable are we using? Is it still x or p?
P.
P. 2p minus...
Okay, so that 2 doesn't have a variable with it, so that 2 is just a constant, and will go away when we derive.
Oh, we're deriving? Okay. So, 0 minus... So that's 1 over... Is it just 1 over 5,000?
Perfect. And that will be negative because of the negative sign, but u prime is negative 1 over 5,000. So that means if I wanted to substitute, this would be, I need a 1 over 5,000 in order to substitute for u prime that I don't have. So I'm going to multiply by 1 over 5,000 and divide by 1 over 5,000 in order to get my u prime. So if I'm dividing by 1 over 5,000, that's the same thing as multiplying by 5,000, right? So this will become 1 over 2 minus p over 5,000 is equal to 5,000 times 1 over 5,000 over 2 minus p over 5,000, or 5,000 times u prime over u. I still have the 1 over 10,000 on the outside, so the 1 over 10,000 is going to stay, the 5,000 is going to stay. And then what happens when I integrate u prime over u?
ln, the natural log of u.
Natural log of u, perfect. Now I would have a plus c on this side. I'm going to move that to the other side. Since I've got a plus c on both sides and they're not the same constant, when we combine them, we'll still have some unknown constant on that side. Okay, that was the hard part. Any questions on how we got here? Okay, I'm going to make some substitutions, and we will solve for p. So just substituting first, t plus c is equal to, this is 1/2 times ln p plus 5,000 over 10,000, so 1/2 natural log of u, which we said was 2 minus p over 5,000. Okay, Andrew, if I want to solve for p, what's the first thing you would do?
I'll set t equals 0.
Set t equals 0. Let me see what our t was. Hold on. We know when t equals 0, our population is 3,000. That would allow us to solve for c if we wanted to here. And I don't think this is the best time to do that, maybe.
Okay.
And because that's going to force us to solve this crazy natural log where I've got a 3,000 over 5,000 here, which is maybe not ideal. So I might wait in order to solve for c. If I'm going to wait to solve for c, then how can I solve for p first? So I want to be able to solve for p in terms of t and c.
Use e to the t plus c power for both sides.
Okay, I could do that in a minute, but in order to do that, I need to get the natural log of something alone on this side. Is there anything that I can multiply both sides by in order to start getting the right into a single natural log instead of two?
ln p to the 1/2 power times
Okay, so you're going to use power property and move these up is what you're doing, I think, right?
yes.
Okay, that's possible. I believe this would be easier right now if we just multiplied by 2 everywhere instead of using power property. Which would also get rid of both 1/2s on that right side. So I'm going to do that, but then we'll go back to your property of logarithms, so you can combine your two logarithms after that. So if I multiply through by 2, this will be 2t plus c. It's still c because we have not solved for that constant yet, so 2 times a constant is still a constant. Equals ln p plus ln 2 minus p over 5,000. Okay, now back to you, Andrew. With properties of logarithms, what is the natural log of p plus the natural log of 2 minus p over 5,000?
Natural log of p times 2 minus p over 5,000.
Okay, so that's the natural log of, if I combine these, I'm going to multiply, so that would be 2p minus p squared over 5,000. Awesome. Okay, and now, since you already said what we were supposed to do for the next step, what's our next step?
Plug t for 0. Plug 0 for t.
If I plug in 0 for t, I'm still going to have a crazy number over here to deal with inside my natural log, so still not yet.
E to the, just, yeah.
There we
use
go.
Use e for both sides.
Use e for the base of both sides, so e to the t plus c is equal to e to the natural log, which will cancel, of 2p minus p squared over 5,000. Okay. If I'm adding a constant, then what are we really doing if I want to break this up? Let me jump over to Eric. How could I rewrite this? I'm adding a constant c.
What do you mean by rewriting the constant?
If I'm adding with the same base, what can I do?
Separate.
I can separate. So if I wanted to separate this, what would it look like?
E to t plus times
Okay, e to the 2t times
ec.
e to the c power. E to the c power is still going to be a constant. Oops, p squared over 5,000. So that means e to the c is still c. So I've got c e to the 2t is equal to 2p minus p squared over 5,000. Okay, and now, Andrew, I don't have any natural logs left, and when I plug in t is 0, I'll be raising to a 0 power, which should make this easier to solve. So this is probably where I would solve for c, personally. And then I would keep going after that to try and solve for p. I guess I'm going to go ahead and do that. So we know when time is 0, our population is 3,000. So when t is 0, this will be c times e to the 0 power, which is 1, is equal to 2 times 3,000 minus 3,000 squared over 5,000, or 6,000 minus, this is 3,000 times 3,000, so that's 9 with 6 zeros afterwards, over 5 with 3 zeros afterwards is a 9 with 3 zeros over 5. So what is that? That is 1800. Six thousand minus 1800. C is 4200. Okay, somebody check my math right now. 3,000 squared divided by 5,000 is 9,000, correct? Divided by 5, 90 over 5 is 18, and then 0, 0 is 1800, 6,000 minus 1800, 4200. I believe that's right. So now that I've got C, I can plug that back into our equation here. And use that to solve for P. I guess I'm just going to keep going down. So that gives us 4200 e to the 2t is equal to 2p minus p squared over 5,000. Okay, what am I looking for? I'm looking for what happens to p if t goes to infinity. Fortunately, I don't see a good way out of this. I can do p over 5,000. by 2 minus b over 5,000 right now. It's not going to help, I don't think. I think I've grouped as much as I can. If t goes to infinity, my left side is infinity. Okay, so I'm looking at this and trying to maximize my population now. If my population is 5,000, then this would be 2 minus 1 is 1 times 5,000 would be my population. If my population is 10,000, then we approach 0 again. If my population is 0, then we're at 0 again. I think we're maximized at 5,000 then. Let's take a look again at our slope. So let's approach 0 at either 10,000 or 0. I need to be double that. I don't actually see where I went wrong. Alright, I'm going to show a shortcut. I wasn't able to get to the same answer with separable differential equations, unfortunately. But taking a look at our logistics equation, dp over dt is equal to p times 2 minus p over 5,000. So right now, if I want my slope to be 0 for my logistics equation, it should look like this. My slope will be 0 if our population is 0, and my slope will be 0 if our population is 10,000. Which means we've got an equation that looks like this, where we had kind of exponential growth for our population, but then either space or food constraints or something else started slowing down our exponential growth until we hit a limit that our environment could support our population. So we call that a logistics equation, where we've got, it's an equation defined by upper and lower limits that models population growth in real life. My upper limit here, we're approaching that upper limit when our population approaches 10,000, which we can see because our slope of this graph, when our population approaches 10,000, is approaching 0. So that's our shortcut, and I should have been able to get there with separable differential equations. I'm not exactly sure where my mistake is. So I may have to take a look at that a little bit later. Sorry guys. Does everyone understand what's going on with the shortcut though? So if looking at our slope.
Yeah. Yes.
Okay. I was really hoping I could prove it, but on the actual AP exam, you guys don't want to solve that with a separable differential equation because you'll be here all day for it. but eventually, if I can go back and figure out where I made a math mistake, that should have worked out. Alright, we'll try one more. So, for 28, I think this one can work for AB as well. So for 28, I want to take the limit as x approaches 1 for this one. If I plug in x equals 1 for the top, Jin, what's going to happen if I integrate any function from 1 to 1? Zero. On bottom, when I plug in 1, I've also got 0. So if this limit right now is 0 over 0, Jane, one more time, what do I need to do? Derive all. Okay, derive top and bottom separately, so that's L'Hopital's rule. So that's what we're going to do. We're going to derive the top and bottom. Deriving the integral from 1 to x of e to the t squared dt over the derivative of x squared minus 1. Kyle, what happens if we derive the integral from 1 to x of e to the t squared dt?
I'm sorry, could you repeat it?
If I derive the numerator, what's going to happen?
Let's see, et squared 2t. Et squared times 2t.
Close. That would be if I derived it without the integral there. But right now I'm deriving an integral.
dt dx d over dx squared.
There's a formula on the formula sheet for what happens if you derive an integral, I think. So if we derive an integral, d over dx of the integral from a to b of f of x dx, what would happen from the formula sheet? Anyone? Okay, so we get f of b times the derivative of our x values. That's the derivative of b prime minus f of a times a prime. And the reason why that happens is because if we think of the integral of f of x as some sort of capital F of x function, then when I integrate this, I'll get capital F of upper bound minus capital F of lower bound, right? But then when I go to derive that afterwards, when I derive this, the derivative of capital F is my lowercase f, so I'll get back to lowercase f of b, but with chain rule I'll have to multiply by b prime, minus derivative of capital F is lowercase f of a times a prime because of chain rule. So Kyle, back to you. What's going to happen when I derive the integral from 1 to x of e to the t squared dt?
Could it be e to the power of 1 times...
Upper bound first. So e to the power of...
Oh, it'll be x squared.
Okay, e to the power of x squared.
Times 1. So...
Okay, so e to the power of x squared times the derivative of x, which is 1. Good. Minus...
minus fa, so e to the power of 1, which I think is just e times 0.
Perfect. And on the bottom, if you derive x squared minus 1,
2x.
2x. Okay, now I need to figure out what our limit was. We were approaching x equals 1. So that means we should be able to plug in our limit. Okay, this was the limit as x approaches 1 was equal to the limit as x approaches 1. So if I plug in 1 right now, what's going to happen?
E over 2.
E over 2. Looks good. Okay, that's all of the ones I think that are on this sheet that are both A, B, and BC. And we are at the 70-minute mark right now. So, Jin, if you want to join us tomorrow, I'm going to go back to the 3 o'clock time because Niall has messaged me and said that he can't make afternoons at all now because of a tutoring conflict. Well, let me re-poll everyone that's actually here. So, do you guys prefer 3 p.m. or 4:30?
3 p.m.
Okay, 3 p.m. for Andrew.
3.
3 p.m. for Eric.
3.
3 p.m. for Kyle. Maybe after 4 p.m. What I might be able to do is, if we can compromise, I could do 3:30, and we would start with BC topics until 4, and then all the AB students could join us at 4 if that works better for you, Jim. So you could come at 4 and catch the second half. Okay, is that okay with everybody from the BC crowd? So 3:30 instead?
Yes.
Yeah, I'm fine with that.
Okay, cool. Thank you. So, Jin, thanks for coming. We'll start tomorrow at 3:30. And I'm going to jump back through a couple of these BC questions that we passed. Okay, starting with this length of a parametric. On 21. Andrew, what's going to happen here?
I should derive both y. I should get dx over dt and dy over dt by deriving both equations.
Okay, so if I derive the first equation, what's going to happen?
Dx over dt is t squared,
Okay,
and dy over dt is t.
Okay, so what's our arc length of what's our length of the parametric equation then?
So since our bound is from 0 to 1, so it should be integral from 0 to 1, square root of t to the 4th power plus t squared dt.
Right. I'm going to write t squared squared plus t squared, but you're right. So that's our arc length is the integral from 0 to 1 of the square root of t to the 4th plus t squared dt. Where do we match? We match at C. Okay. I am checking as we go this time, as soon as we finish, so everything's been right so far. 22. If our limit as b approaches infinity of the integral from 1 to b of dx over x to the p is finite, then what has to be true? So if we have a set answer for our integral, then what must be true? Eric, what do you think? Eric, are you with us? Okay, I might have lost Eric, so I'm going to jump over to Kyle. So this is our integral test. We proved that with the integral test we get a finite answer. So which of the following must be true?
I took a guess
Mm-hmm.
and guessed A.
Okay, A is correct. So with the integral test we get a finite answer, then that sequence should converge, right? And that sequence is x raised to 1 over x raised to the p power, which is the same thing as 1 over n raised to the p power from starting from n equals 1 to infinity. Okay, it did not diverge, so it can't be B or E. For C and D, I've changed our formula from 1 over x to the p to something different. I've taken out terms. So I don't have enough information to prove that that would still converge. Only because that's not what we integrated. Okay. For 27, we've got a Taylor series that converges to f of x for all real x. I want to know what the derivative would be at 1. And so if I take this general form and we derive, what's going to happen? Andrew?
Oh. The general form?
Yep.
Then it will be the general form, you mean the f and f to the nth power of x, something like that.
So right now this is f of x is equal to this series.
Yes.
So if I wanted to know what f prime of x would look like in general first, and this would be the sum from n equals 0 to infinity of what?
N times a n times x minus 1 part.
X to the n minus 1, okay. So we multiply by the power, and we multiply by the power, took out 1 from the power, so power roll. And then I want to figure out what's going to happen when x is 1 for our answer. So our derivative when x is 1 should be what happens when I replace x with 1 in our sequence. So I'm going to sum up from n equals 0 to infinity n times a to the n times 1 raised to the n minus 1. What is 1 raised to the n minus 1?
1 raised to n minus 1. It will be 1.
1. Even if this ends up being 0 or negative, then it will still ultimately be 1. So when I plug in n equals 0, this will be 1 raised to the negative 1 power, which is 1 over 1. This is still 1. When it's 0, anything raised to the 0 is 1. When it's anything else, this is still 1. So this is the same thing as the sum from n equals 0 to infinity of n times a to the n power. Okay, we don't perfectly match any of ours, so since some of these are starting from 1, I'm going to see what happens to our first term when we plug in, to see if we can get rid of it and start at 1 instead. When n is 0, what happens?
It will start from 0.
When n is 0, the sequence is 0, so
Yes.
if I wanted to start at n equals 1 instead, that would not change anything for my formula. So this is okay too. And now we do match D. Any questions on 27?
No.
Alright. So that's it for all the multiple choice. I have 10 minutes left. I think I might actually call early, so I don't think we have enough time to run through the 5th FRQ that I was asked to run through. So I'm going to save that for tomorrow, but we'll start with that instead. We'll run through the 5th FRQ, I'll jump back, we'll do some of the AB multiple choice from 1998 that wasn't the same. And then if we've got any extra time, I'll start going through the this graphing calculator section. Alright, so thanks a lot for coming, and I will start tomorrow at 3:30 instead.
Okay.
Okay.
Mr. Brandon,
Yes.
can you post the parents' test answer key for BC examination?
Okay, so you guys should have access to the book online.